Hello and welcome to this tutorial. In this tutorial, we're going to be looking at pressure volume or thermodynamic cycles. Thermodynamic cycles represent a series of thermodynamic processes that get repeated, hence they're called cycles. Please remember to pause or rewind this tutorial as you need to. Let's begin. Basic cycle, my grain elevator. So this particular example is given to you in an analogy form that will try and help you to connect these concepts and ideas. Please remember that, not only are some of these not very realistic, but also the, temperatures, pressures, volumes also may not be realistic either. So don't worry so much about that. The numbers are presented to you to make the math easy and mental math oriented. Part 1. Consider a giant cylinder of gas capped by a piston that can move up or down in a cylinder without friction. Grain at the low elevation waits near the pitch house. Another pitch house rests on the piston in the cylinder of gas. So you can see that here and here. The gas has an initial volume of 20 cubic meters, an initial pressure of 50 newtons per square meter. And by the way, Newton per square meter is the same thing as a Pascal, by the way. Okay. I'm going to keep it in this unit here, but know they are interchangeable units. And a temperature, initial temperature of 30 Kelvin. Okay. So what is the volume, pressure, and temperature at point A? Well, we're given point A is those initial values. So let's go ahead and note that. Okay, so V is 20 cubic meters. Pressure is 50 newtons per square meter. And temperature is 30 Kelvin. Okay, so that's the first part. That's where we're starting. Now, it tells us in this process from A to B, it says, as grain is pitched onto an elevator, heat is added to the gas. The elevator does not move up. Well, that means the volume stays constant, but the pressure quadruples. Okay, well, let's figure that out. So the volume does not change because it said the elevator does not move. So the volume stays at 20 cubic meters. The pressure, however, quadruples. So 4 times 50 would be 200 newtons per square meter. And how is the temperature going to be affected by that? Well, remember, ladies and gentlemen, that temperature is temperature is proportional to pressure times volume. So what happened here was the volume did not change, but the pressure increased by 4 times. It quadrupled. So if the volume does not change, that means the temperature quadruples. But what is 4 times the original temperature? 120. So the temperature is now up to 120 Kelvin. Okay, now let's look at part C. From B to C. So once the grain is fully loaded, the elevator door is shut. Heat is added to the gas, causing the piston to rise. Now the volume has increased. So during this process, the volume triples. However, what happens to the pressure? Well, again, we talked about this last time when we learned about thermodynamic processes. See, pressure is the thing that's holding up the piston. It's the collision of the gas molecules, right? But the pressure from below has to balance the pressure from above, which is really due to the weight of the house on that cylinder. Since the weight of the pitch house doesn't really change because it's the same amount of grain, you have the same pressure from above, which means you have the same pressure from below. So the pressure will not change from B to C. So what does this mean? The volume has tripled. So triple 20, we're now up to 60 cubic meters. The pressure has stayed at 200 newtons per square meter. And the temperature has gone up yet again, because now, again, we can go back to temperature is proportional to pressure times volume. See, if we look at the temperature from the previous point B, the pressure stayed, okay? So that's a 1, but the volume, it tripled. So the temperature is going to triple, or you could say 120 is going to triple. So triple 120 would be 360. Now that's one way to look at it. Another way to look at it would be if we looked at the pressure and volume from the original 30. So from the original 30, okay, what's happened? The pressure has gone up by a total of 4. The pressure has quadrupled, right? And the volume has tripled, which means the temperature is 12 times greater than that, okay? Either way, you're going to get the same value, which is 360 Kelvin. Okay, now what happens at point D? Let's read. So from C to D, it says once the piston reaches the high elevation, the heat is now turned off as the grain is pitched off the elevator. Now, if the grain is pitched off the elevator, that means the elevator is less heavy. That means there is less pressure from above. That means there's less pressure from below. So the pressure is reduced. Now, specifically, it says reduced to its original value, okay? But you can see that the volume from C to D did not change, okay? The volume stays constant this time around. Okay, so let's make some notes here. The volume stays at 60. The pressure reduced to its original, which was 50. Okay, and the temperature, okay, would correspond to what? Well, if you think about this, if we use the previous model, okay, temperature is proportional to pressure times volume. Think about what happened. The volume stayed constant, so the volume stays at a 1. The pressure, on the other hand, decreased and dropped by 4 times smaller. That means the temperature is 4 times smaller. Well, 4 times smaller than that. But what is 4 times smaller than 360? That would be plot the cycles on the pressure volume diagram that follows. Okay, so we started at A, which was 20 and 50. Started right here. Okay, there's A. All right, and it had a temperature, by the way, of 30 Kelvin. Okay, and then what happened here is that the pressure went up to 200, keeping the same volume. Right, and the temperature went up to 120. Okay, this is the process from A to B. Okay, then what happened is the pressure stayed constant, but the volume tripled from 10 to 60. All right, so tripling 120, we're now at a temperature of 360 Kelvin. And then finally, the pressure reduces by 4 at a constant volume, bringing the pressure back down to 50 at state D. But you've just brought the temperature down by 4 also, which is at 90 Kelvin. And then completing the cycle would bring D back to A again, which was the original 30 Kelvin. Okay, part F, how much work is done on the gas in each process? Well, I can start this off by saying the work done from A to B and the work done from C to D are both zero. Okay, why is this? There is no change in volume in each case. Remember, work is a pressure times a change in volume. So if you have no change in volume, you have no work done. Okay, so part 1 and 3 are pretty easy. Now, B to C. Well, B to C is an expansion. So work on an expanding gas is negative. So pressure times a change in volume. What was the pressure? It was 200 newtons per square meter times times the change in volume, which goes from 20 to 60. So the change in volume is 40 cubic meters. Okay, and 2,000 times 40 would be negative 8,000 joules of work done on that gas. Okay. Now for part 4, from D to A, the work done from D to A is work done on a compressed gas. So that's going to be positive pressure times the change in volume. So the pressure is at 50 now. The change in volume is still 40. Now I know it's going from 60 down to 20, but remember, you're compressing the gas. So compressing the gas, and you're increasing the energy of the gas, and an increase in energy is considered positive work. Well, this would be 2,000 joules done on the gas out of the work rate. What was the net work done on the gas? Well, net just means total. So how do I find net? It would be the work from B to C. Well, technically, it's the work from all of them. So I mean, I guess I should be a little more specific. It's the work from A to B plus the work from B to C plus the work from C to D plus the work from D back to A again. So it's 0 plus negative 8,000 plus 0 plus 2,000, which is equal to negative 60,000 for the entire cycle. Part G, the molar specific heat capacities are CV equals 3 halves R and CP equals 5 halves R. How much heat was added or removed in each process? Hint, PV equals nRT. So we're looking for how much heat. So we're going to use that equation. Q is equal to N. Now from A to B, it's isovolumetric. Remember, the volume didn't change. So from A to B, we're going to use NCV delta T. So what I'm going to do to find delta T, okay, what I'm basically going to do, I take my ideal gas law equation, and I'm going to kind of do it over here to the side so you can see, and I'm going to solve for T. Well, solving for T, I get PV divided by N times R, right? So T2 would be P2 V2 over NR. P1 would be P1 V1 over NR. Why do I say this? Because delta T would be T2 minus T1, or it would be P2 V2 over NR minus P1 V1 over NR. Or one more way you could look at it is you have a common denominator here. So really, it could just be P1V1 or P2V2 minus P1V1 all over NR. Okay, so I'm gonna use that. So we've got N times, now CV is 3/2 R. Okay, and then I have P. In this case, it would be P B B minus P A V A all over N times R. Why do I show it this way? Because this cancels, and what we're really left with, guys, and this is a nice little shortcut, we are left with Q is equal to 3/2. Notice the volume didn't change. So it's 3/2 a change in pressure times volume. So 3/2 times, how did the pressure change? Well, the pressure changed from 50 to 200. So the actual pressure change is 150. Okay, the volume was at 20, I think. Yeah, 20. Okay, and if you multiply that out, half of 20 is 10. 150 times 3 would be 450, times 10 would be 4,500 joules of heat. If it's positive, right, heat has been added. Okay, now part 2, B to C, was same idea, but now it's isobaric, excuse me, because now the pressure stays. So how does this one do? Well, Q is equal to NCP delta T. Now look how this one's going to work. We've got N, CP is now 5/2 R, okay, times the pressure at C, volume at C, minus the pressure at B, volume at B, all over N times R. Notice, ladies and gentlemen, this is really the same as what I derived over here, but instead of using 1 and 2, I'm going from B to C. That's why C is the final and B is the initial. Okay, now we can see N cancels, we can see R cancels, and what we end up with, ladies and gentlemen, is we end up with Q is equal to 5/2. Now this time pressure didn't change, so it's 5/2 pressure times a change in volume. So we're going to go 5/2 times the 200 Newton per meter pressures times the change in volume, which was 40. It went from 20 to 60, right? So the change in volume of 40. All right, let's go ahead and compute that out. Let's see, half of 20 is, half of 40 is 20. Let's see what we got here. 200 times 5 would be 1,000. 1,000 times 20 would be 20,000 joules. Again, since the answer is positive, heat is being added in this process. All right, C to D. Now I'm going to use the shortcut now that we developed it. C to D is isovolumetric, just like A to B was. Okay, so isovolumetric had 3/2 times the change in pressure times the volume. So it was 3/2 times what's the pressure? The pressure is going from 50 to 200. That's negative 150, okay, times the volume of 60 cubic meters. Well, half of 60 is 30, okay, and we can go 150 times 30, which would be 4,500, times 3 would be negative 13,000 500 joules. Since the answer is negative, we're talking about heat is removed during processing heat. Now, D to A is also isobaric like B to C was. I'm going to use the shortcut that we derived earlier, and we're going to go 5/2 P delta V. Okay, and we're going to go 5/2 times the pressure stays at 50. Okay, and the volume goes from 60 down to 20. So the change would be 20 minus 60 or negative 40. Okay, so half of that would be negative 20 times 250 would be negative 5,000 joules. Again, since the heat is negative, we're talking about heat is removed during this process. Okay. So what was the total heat added from A to C? Okay, now what this would be from A to C, it would be the heat from A to B plus the heat from B to C. That would be the total heat added. So I'm going to basically take my 4,500 joules plus my 20,000 joules, right? And I get 24,500. Okay, so total heat added. What was the total heat ejected or removed? Now we're going to go from the heat from C to D plus the heat from D back to A again. So this one would be essentially negative 13,500 plus negative 5,000, right? And we end up with about negative 18,500 joules removed. Okay. Now it is asking, technically the question is asking what was the total amount of heat ejected from C to A. Heat ejected will be a positive value. So I mean, we're really talking about the absolute value of the heat, but realistically, if heat is removed, it technically is a negative quality. Part 7, more heat was added than ejected during the cycle. Account for the difference, explain what happened to the heat that was added but never rejected. So what we can say for this is that the heat that was added but never ejected became mechanical work. That's exactly what thermodynamics is all about. It's converting heat energy into mechanical energy. But it was specifically the work done by the engine during the entire cycle. What was the efficiency of the heat engine? Okay, now there's a couple different ways we could do it. Efficiency, if you understand it, is the percentage of how well an engine does work. Okay, because that's what it's designed to do. It's designed to convert heat energy into mechanical energy, which is work. So we would take the work divided by the total energy coming in. We're going to get the mechanical energy or the efficiency of mechanical energy done. So one way to calculate this would be the work that was done for the entire process, which would be the network. Remember, we had a network of negative 6,000 joules here. Okay. Now, I'm not going to worry so much about the negative sign, okay, because, again, we're talking about like an absolute value. We have 6,000 joules of work total done, and the net heat coming in, okay, the QH is the heat coming in, and that was the 24,500 joules of work. So go ahead and divide those two, and we get 0.24. But we always have to write efficiencies as a percentage. So we have to move that over twice. And we can see that this engine is 24% efficient, which means it's 70%, 76% inefficient. It's losing 76% of heat to the environment. Now, another way to calculate this would be to take the fact that work is equal to the heat coming in minus the heat going out over the heat coming in. And we can split this up into separate denominators. QH over QH is 1 minus QC over QH. So we have two different calculations that we can do. 1 minus QC over QH will give you the same value. So 1 minus, and now QC is the heat going out. Okay, so 18,500 over 24,500. So if we divide those two, okay, and then go 1 minus that, we're going to get the same value, 0.24, right, or 24% efficient. Okay. In the next part, we're going to take a look at maximum theoretical efficiency. So a more efficient cycle, the Carnot engine. Next to that, I'm going to label this Carnot engine. The Carnot cycle represents maximum theoretical efficiency, not necessarily actual efficiency. And you're going to see why. So consider a cylinder of gas going through the following cycles. The initial conditions are 240 newtons per square meter, 20 cubic meters, 360 Kelvin. We're going to start by plotting those, by the way. Plot 240 and 20 on this graphic. So 240 and 20 would be right here. Okay, that's our initial condition, which we're going to call A. All right, so now let's read what happens. So from A to B, as the story begins, the piston is rising. It had a head start in a sense that it was already moving up before we saw it. But 6,545 joules of heat are added, nonetheless keep it motivated. Since gas is expanding upward faster than the heat would be forcing it to, the pressure is dropping. It drops half of its original value while the volume doubles. The temperature remains constant. Remember, ladies and gentlemen, temperature is proportional to the change in pressure times the change in volume. Well, the pressure is cutting in half. The volume is doubling, right? We get a temperature coefficient of 1. What that means is the temperature doesn't change. And that's exactly what it says here. The temperature doesn't change or remains constant. All right, so how do we do this? Well, we're going to take the pressure, we're going to take the volume and double it, and we're going to take the pressure and cut it in half. So what would that look like? Well, on the picture here, what that would mean is, and we can kind of spell it all out, just to make it easier to graph. So from A, we have a pressure, volume, and temperature, and then we'll do the same thing at B, C, and D. So initially, we have a pressure of 240, a volume of 20, and a temperature of 360 Kelvin. Okay, now what happened to that information at B? So at B, the pressure cut in half. So the pressure is now down to 120. The volume doubled. So the volume is now up to 40. Okay, what happened to the temperature? It did not change. It stayed the same temperature. Now let's plot those values. So we're plotting a pressure of 120 and a volume of 40 would be exactly right. Okay, and we're going to make it curve a little bit. This right here would be isothermal expansion. Okay, isothermal because the temperature at A is 360, the temperature at B is 360. All right, let's figure out what happens at C. Now, from C to D, the heat is removed. The pressure contracts to half. I'm sorry. I missed one. B to C. Sorry. So from B to C, the heat is turned off. So we have no heat added to the system. But the piston continues to rise. That means the volume is going to go up. The pressure continues to drop. Now, the pressure is going to be 1/30th of its original value, and the volume is going to increase 2.5 more. Okay, let's figure this out. The volume is 2.5 times more than this. So we can say, what is 2.5 times? 2.5 times the original value right here. So 2.5 times A. Later. Okay, so 2.5 times the original volume of 20 would be 50. 50 cubic meters, and 1/30th of the original pressure. Well, if you take 240 divided by 30, you're going to get 8 newtons per square meter. Okay, now what happened here? What we're going to do is we're going to take the temperature of 360, right? And we're going to essentially multiply it times 2.5 and divide it by 30. And you'll see that the temperature went down to 30 Kelvin. And we can plot that by doing the following. So 30 Kelvin, excuse me, 50 is over here, okay? But the pressure is pretty hard to see. The pressure is 8. Well, this is 40. That means this is 20. That means half the first box is 10. That means less than half the first box is 8. This point is right there. That's point C. And the temperature at C is now down to 30 Kelvin. And we would represent that with a much steeper curve. This is adiabatic expansion. And no heat added. Here, heat is added. Okay, now from C to D. So from C to D, heat is now removed. The gas contracts to half its previous volume. The pressure doubles its previous value, and the temperature remains constant. So what would that be? Well, that means okay, so if the pressure doubles, it's now up to 16 newtons per square meter. The volume is going to cut in half. So half of 50 would be 25 newtons. Sorry, wrong unit. 25 cubic meters. And how does that affect the temperature? Well, it said the temperature remains constant, so the temperature stays at 30 Kelvin. So plotting that last point, okay, we are cutting the volume down to 25 and the pressure is up to 16. So we can see that this point here would be about, right here, this would be about 20. So, and this is 10, so 16 would be about 3/4 up on the box, something like that. So we can plot this point maybe about right there-ish. Okay, and that would be D. The temperature at D is still 30 Kelvin because it's isothermal. And we have a nice flat curve all the way up to D. And then the process to make it a cycle would bring it up back to A again. So this here, this would be heat loss or heat removed. Okay, and this is isothermal compression. As you can see, the volume is getting smaller. Where this over here is adiabatic compression, where there's so much work done to increase the internal energy and the temperature of the gas, but no heat is added during that last cycle from D to A. All right, so what's the Carnot efficiency of this engine? Well, we can find the Carnot efficiency by going 1 minus Tc over Th, meaning the Carnot or maximum theoretical efficiency is based on the high and low operating temperatures of the engine, not the heat in and out of the engine, but the operating temperatures of the engine. So we're going to go 1 minus. Now the lower temperature would be 30 Kelvin. The higher temperature is 360 Kelvin. Okay, and I think that's like 0.083 if I remember right. But you've got to take the quotient 30 over 360, go 1 minus that. Okay, now when we do, we're going to get out 0.92 or 92% efficient. That's pretty darn good because that's telling you that we're only losing 8% of energy to the environment. We're using most of the energy coming in to do work. Now, how much work was done on the gas? Well, we could do this a couple ways. From A to B. We could use the first law of thermodynamics. Okay, in which case the change in internal energy was 0 because there was no change in temperature, remember? And internal energy changes as temperature changes. Okay? Because internal energy is basically the kinetic energy of the gas, and average kinetic energy is measured by temperature. So as if there's no change in temperature, there's no change in internal energy. And if we kind of whip this around a little bit, the work is equal to the negative of the heat from A to B. Well, the negative of the heat from A to B would be essentially negative 6,545 joules, because that's the heat we were told that was added to the system. So we can do it that way. Okay, that's one way to do it. The other way, no, I guess that pretty much is the way we're going to use first law of thermodynamics. I was thinking of something else, but that's not going to work for this point. So yeah, first law of thermodynamics will help us figure out the heat that was, using the heat, that was added. The work done on the gas is negative. Now, why is the work negative here? What's the meaning of the negative? Well, remember, from A to B, we have isothermal expansion, and as the what's happening there is that it's expanding really slow. So although the volume is getting bigger, the internal energy of the gas is not changing because the temperature is not changing. Okay, so what has to happen is there has to be a balance point. If the internal energy is not changing, and we can see it here, that means that any heat added, right, has to be balanced by work subtracted, hence the negative right there. Okay, negative work done on the expanding gas. How much heat is ejected from C to D? Well, we can't really use first law for this because although from C to D, you do know from C to D it's isothermal. So from C to D, you do know the change in temperature and thus the change in internal energy are 0. But the problem is you don't know the work done from C to D. So since we don't know that, that's too many unknowns, right? So if we try using the first law, okay, we do know this, but we don't know those two. So that's too many unknowns, okay? That's not going to work. But what will work is if we create a proportion, okay, and the proportion is basically going to look like this. What it's basically going to do is it's going to assume the actual efficiency is the Carnot efficiency. What that basically means is the actual efficiency is 1 minus QC over QH. And we're going to set that equal to the Carnot efficiency, which is 1 minus TC over TH. Now, if you look carefully at what happens here, the 1 is going to cancel, the negatives are going to cancel, and we basically get this ratio QC over QH equals TC over TH. And you can, solve, we're solving essentially for QC. Okay, we're solving for the heat ejected. So we would multiply both sides by 2H. So QC is going to be TC times the QH that you multiply both sides by. Okay, you understand what I'm doing here? I'm trying to multiply both sides by QH, like that. So we go TC times QH divided by TH. So let's go ahead and plug into that. TC, the colder temperature, would be 30 Kelvin. The higher temperature would be 360 Kelvin. And the heat coming in, if you forgot, go back and look. Okay, but the heat that's coming in go back and take a look here. There we go. The heat added. Well, how much heat was added? Well, it tells you right here. 6,545 joules of heat are added to it. So that's going to be our value right there. That's pH. 6,545 joules. Kilograms. And when we multiply 30 times 6,545 and divide it by 360, we're going to get 545 joules of heat expelled from the heat engine. Okay. What was the net work done by one cycle? Well, we could find this a couple different ways. Okay, one way we could do this is using the first law of thermodynamics. So we could say that since for a whole cycle, the change in temperature is 0 because you return to the same temperature you started. So there's no difference in temperature for a full cycle, which means there's no change in internal energy, which means the work done on the engine for the whole cycle, okay, is equal to the negative of the work. So the work done on is equal to the negative of the heat, because I have to subtract heat. But we're talking about the net work done by the engine, which is equal to the positive heat, the positive net heat, okay? Which is basically what? It's your, you go back to our heats that we calculated. Go find this work that we did. Sorry, it was so we have the heat coming in, which is the 6,545, and then we have the heat going out, which is the 545. So that would technically be minus. Okay, so it would be 6,545 plus a negative 545, negative because heat is removed, right, or expelled, and that adds up to a total of 6,000 joules, right, of work done by the cycle, by the engine. And that's one way to do it, is just use first law. Use first law of thermodynamics for the whole cycle. Another way, an easier way, I think, is to take the fact that the heat engine is simply the heat coming in, right, is the heat going out, which is 6,545 joules minus 545 joules, right? And you see stuff. Okay, I hope you found this video tutorial to be helpful. Remember to pause or rewind the video to any points that you need to. See you next time.